So we were at this point last time where the ideal I alpha beta was defined as the product of I alpha and I beta, and rather I alpha we could prove to be product of I alpha and I beta, and I'd given this as an exercise. Now let's look at as our next example I alpha, which is all functions that vanish on alpha. This is an ideal, and I claim that this is a maximal ideal. Of this ring F. Do you see the proof of this? So what do you need to show to conclude that I alpha is a maximal ideal? Any ideal that contains properly I alpha is the entire ring, which means it contains 1 as well, the identity.
That contains I.
No, it is contained in I alpha. I alpha comma beta is actually contained in I alpha intersection I beta. So it's a very simple proof, but it's a instructive proof. So let's say let some G be in F and G not in I alpha, which means that G of alpha is not 0. Okay. Now consider this ideal. So this is an ideal which certainly contains I alpha, and it contains this one extra function G, and whatever is the ideal generated by that. Now let's pick up an F in I alpha such that f of alpha is 0 and f of beta is G beta minus G alpha. In this ideal, let's say G hat to be G minus F. That's simple calculation. That G hat of beta is a fixed number, which is non-zero everywhere in the interval. So G hat beta or G hat is a function that is not zero anywhere in the interval and actually is a fixed value. So I can define it as, and G hat is in this ideal. By its definition is G minus F. And G hat is simply the, well, not quite G hat, but 1 is 1 over G alpha times G hat. So this shows that I alpha is a maximal ideal. See, there is this nice connection that all the functions that, the ideal of all functions that vanish on one point is a maximal ideal. And we'll extend this a little later, but for now, let's stop here with examples and let's look at two special kinds of quotients. Particularly, let's start with maximal ideal, and let's start with any ring R. Then you look at the quotient R by I. This quotient ring has very special structure because I is a maximal ideal in R. And the special structure is that every non-zero element of this ring is a unit. Typically in a ring, units are a few. Most of in the examples we have seen, most of the elements are non-units. But this is a ring where every non-zero element is a unit. How do you prove this? Let's pick up an element. So let A plus I be in R quotiented with I. This is this typical element. So this A plus I is a non-zero element in this quotient ring. The element the I is that corresponds to the zero element. Now I is a maximal ideal in the ring R, and A is not in I, which means that if you add A to the ideal I and look at the bigger ideal, this ideal, this is the whole ring. Which means in particular one equals some B times A plus T. Since these two rings or these two ideals are the same, that means the element 1 which is in this ideal is also in this ideal. The element 1 being in this ideal simply means that it is of this form, B times A plus some T being in the ideal I. So now consider this product. This is an element of the quotient ring, B plus I. A plus I is an element of the quotient ring. What is their product? It is BA plus I. And what is BA plus I? Look at this equation. This is an element of BA plus I. So that means 1 is in this. This is 1 plus I. It's a simple proof, but it is making use of the properties of this quotient ring, that if two elements differ by an element in the ideal I, then they belong to the same equivalence class. So here 1 and BA differ by T, which is an ideal I. So the equivalence class BA plus I and 1 plus I are the same. This is the identity in the quotient ring. So this is all we need to prove, that A plus I is a unit because there is an element B plus I whose product with this is 1 plus I. This is existential argument, yes. Well, constructive argument, well, it won't necessarily, it will be, can be formulated in terms of constructive argument, but then we'll have to go into this, the generators of the ideal itself, I itself, and how do you construct the general element of that ideal, because then you use the generators of the ideal I and then write everything in terms of that. It depends on the ring R. How complex is this ring? If the ring R is simple, then the finding inverse is easy. If it is not simple, then it's going to be more difficult. So this proof generalizes to all rings. Doesn't matter what the ring is. That's why the existential argument is better. This also means that in this quotient ring, there are no non-trivial ideals. Every ring has these two ideals. The ideal of 0, which is just contains 0, and the ideal 1, which contains the whole ring. This quotient ring has no other idea, because any other element, any non-zero element, if it is there in the ideal, then since it's a unit, then the entire ring will be in that ideal. So that ideal is 1. Now these are very special kind of rings, and these are called fields. All non-zero. Examples? Set of rational numbers is a field. All non-zero elements being units is equivalent to saying that division is possible in the ring. You can divide by, so because if you have element A, then 1 by A is also in the ring, because since A is unit, so there is a B, such that B times A is 1, so B is 1 by A. So if you have to divide by A, you simply multiply by 1 by A. And so complete division is possible. And we already know that in rational, complete division is possible. Except by division by 0 is not possible. Division by any non-zero element is possible. Other examples? Yeah. Real numbers, complex numbers, absolutely real numbers, complex numbers, these are all fields. Any other example? Z is not a field. ZP is a field, yes. ZP is a field, where P is prime. Why is ZP a field?
Every element AB is common into one mode.
Yeah, we can invoke that, but we can invoke that just the previous theorem also.
P is prime ideal, maximum ideal.
P is maximal ideal. See, ZP is isomorphic to Z quotiented with the ideal generated by prime number P. Now this is a maximal ideal if P is prime. And so the quotient of the ring Z with this is field. Any other example?
Non-singular matrices.
They don't form a field. Not just commutative. If you add two non-singular matrices, the result may not be non-singular. But then it's not a field. It has to be a ring first. Here is an interesting polynomials. No, polynomials won't be a field, but a quotient of two polynomials. If you collect all, which are called rational functions, they form a field. Yes. So for example, let me write that. This is, for example, you can take any field f, and you take xn. This stands for all functions of this form. So take polynomials p and q in this ring. This ring we know, f bracket x1 to xn. This is the ring of polynomials, coefficients coming from the field f and the variables being x1 to xn. Take two polynomials p and q and take their quotient p by q. Q should not be 0. This is a field. Why? This is a ring because you can add two such functions and you get a function in here. It's a commutative group under addition. You can multiply also. And there is a multiplicative inverse here. P by q is, multiplicative inverse is q by p. As long as this is not a 0 polynomial. P should not be, so otherwise it's a 0 element, right? If p is 0, then it's 0 element. Sorry. All constant, that's under field f anyway. Then it won't be. If this was a ring R, then there is a problem, yes. And that we're taking care of by, it's a very trivially. This is exactly the same way we go from integers to rational numbers. It is the same process. Okay, so these are called, as somebody pointed out, that these are called rational functions. Ratio of two polynomial functions. It's a very good question. That is there a ring whose maximum and the maximal ideal, so that is the quotient of that? That's a very good question, and the answer is, in one sense, it is trivial, but if we don't get into trivialities, then it is not always true. For example, the rationals, we cannot always say that the rationals we can view as a ring and the maximal ideal and the ring and the quotient, that maximal ideal. Well, that's trivial way, because you're starting with q. That's what I wanted to eliminate. Otherwise, qx quotiented with the maximal ideal generated by x, of course, that's q, but that's not that's cheating, because you already defined q. In fact, there are three ways of creating fields from rings. One is take a maximal ideal quotient, that gives you a field. The other two ways, they are specialized, they don't hold for all rings. This Q and F, the fourth example, they are constructed using that way, and that's through the following. Suppose we start with an integral domain as a ring. Then we let f be a by b, a b in R, p not 0. So just take the quotient of pairs of elements. So f has a by b, a b in R. This is a field. Why? Just verify the additivity and multiplicativity. A1 by B1 plus A2 by B2 is this. This is an element of the ring. B1, B2 is an element of the ring. And since I is an integral domain, B1, B2 is not 0. Since we started with B1 and B2 being not 0. Similarly, A1 by B1 times A2 by B2 is A1, A2 by B1, B2. Again, B1, B2 is not 0, so it's an element of F. And all other properties followed pretty straightforward. This is the only two places where I need the fact that R is an integral domain. And this is exactly how we formed rationals and this field of rational functions. Z is an integral domain. F bracket x1 to xn is also an integral domain, and that is why we could do this. And the third way is to extend a field. Look at C. We derive the motivation from there. How do you create C? Also, although it, in a sense, it is falls back to that quotienting. So it is basically Rx quotiented with x square plus 1. This is isomorphic to C. So this way actually is the same, one could say that, as the quotienting. How do you create R? That's trickier. How do you create R? How do you create R? How do you, yeah. So basically we start with, let's say, Q, and we want to create R from Q. If we can do that, then we'll have a complete picture that fundamentally we have integers. And then from starting with those integers, we are now creating by certain operations all of this. Q is just that fractional field. And then from Q we can go to R go to C is by this quotienting. Yeah, that's the question. How do you do that? In fact, what are real numbers? Do any of you know the definition of real numbers? Okay. But there is a slight problem with that definition. So for example, the number 0.999999 forever and 1.00000 forever are these distinct numbers. They are distinct. Why? Okay, let's look at that. Fine, let's look at that. Let us say an be summation j from 1 to n so Bn is just number 1. This represents at 1 or 1.0 all zeros. An is 0.999 n times, n of n nines are there. That's what this definition means. Okay? So we have two infinite sequences. A1, A2, A3 up to all the way. These are infinite sequences. And B1, B2 to B infinity, these are infinite sequences. What is An minus Bn? Or Bn minus An, let's say. Oh, sorry. Should have written J here. One minus 9/10 is 1/10. 1 minus 0.99 is 0.01. 1 minus 0.999 is 0.001. So this is the general form of the difference. Fine. Then what is the limit of the difference as n tends to infinity? In fact, I don't even need to take the absolute value because this is always positive. So I can simply write this as limit of the difference. Mhm.
4x is 0.999, and 10x is 9.999, 10x minus x is 9.
Yes, that's another trick. So x is 1. That's another way. So these two are the same numbers. No, because this number an is an approximation of the number we really are looking at, 0.9999 forever. So to construct that number, I have to look at n going to infinity, and when n goes to infinity, this difference is 0. So there is this confusion that, in the sense that we have this decimal notation of real numbers, does list all the numbers, but it seems to be listing a number more than once. So then we have to worry about, okay, which numbers are equal in this sequence, which are not equal, and only the non-equal numbers are the ones that we want. So it's not a very neat representation of real numbers, although we use it all the time. But if you think about it, we only use rational numbers. We never use real numbers. So, but if you really want a real number, then this representation is not a very good one. And so, the defining real numbers in this sense, in this way, is also not very appropriate. So, in fact, this problem troubled the mathematicians of ancient times, 17th, 18th century, because that's when they realized that real numbers exist, there is irrational numbers. So firstly, the belief was that there are only irrational numbers. Then it was pointed out that square root 2 is not a rational number. You can prove that very easily. And that was considered as a huge shock, because until then nobody had even thought about this. And then people started, okay, then square root 2 certainly is a number. So what kind of number it is? That's when the irrational number and the real numbers were introduced. But then one needed a very clean definition of real number. Okay? And that was given by Cauchy. So since we have got into this, although I didn't want to, let me complete this story. What Cauchy did was he defined Cauchy sequences. It is a sequence of infinitely many rational numbers. A slightly complicated looking definition, but if you think about it, the meaning will become very clear. This infinite sequence of rational numbers, an, is called a Cauchy sequence if for every epsilon greater than 0, no matter how small epsilon is, there exists a large enough n, capital N, which I am calling. So in that I am dropping essentially the first capital N minus 1 numbers from this sequence and considering the numbers after that. The difference between a capital N and a m plus capital N for any m is less at most epsilon, which essentially saying that if you first drop the first capital N minus 1 numbers, look at the difference of any pair of numbers in the remaining sequence, that difference is very, very small. It's smaller than epsilon. And this epsilon we can make as small. Pick any small epsilon, there will be a large enough n beyond which the difference between any pair of numbers is less than epsilon. So which is saying essentially one of the conclusion of this is that if you look at the limit of this sequence, there it is informally at least converging to some number, because all the numbers become closer and closer to each other, and so it starts converging to a particular number, and the number it converges to is a real number. So an example of this is just this, for example, this 1 by 10 to the power n. This is a Cauchy sequence. Why? Pick any epsilon and then the difference, so beyond, let's say, difference of 1 by 10 to the m plus n, 10 to the n, this difference in absolute value is at most how much? At most 1 by 10 power n. So for any epsilon, I can always choose a large enough n, capital N, so that the difference is less than epsilon. What does this sequence converge to? 0, right? It's going towards 0. On the other hand, if you have this Cauchy sequence, let's say okay. So if you have this sequence, does this look familiar? Firstly, this would be a Cauchy sequence. I am not, essentially I am in the numerator here is the decimal expansion of pi. So there's 3, 3.1, 3.14, 3.141, 3.1415 and whatever the extension of pi is. The difference between any two, after beyond a point, the numbers is very tiny. It just really goes to, becomes smaller and smaller. And this converges to pi. Yes. That's why this expansion will be infinitely long. So you have infinitely, for every successive digit in the decimal expansion of pi, you will have one number here. Each one of this number is a rational number, and it is getting closer and closer to the number pi. Fine? Which definition? Yes, yes. That problem exists here also. Yes, but it is, we have to then also say which we have to classify that which of these numbers are not unique and they are equal. So we have to create equivalence classes of these real numbers which correspond to a unique number. Right? So we'll need a way of clearly describing, this. After all, when we say real numbers is a field, we want one element to represent a unique, one representation to represent a unique element. Whereas in this representation, there are not uniqueness property is not there. So of course we understand what real numbers are. There is this real line and every number in there is a real number, but that's an informal understanding. When you want to formally define it, you would like to do it in a very precise way which gives a unique representation for every number. That is lacking in that representation. So that's what Cauchy did. I'll continue with this tomorrow.